Welcome everyone to the third tutorial of electromagnetic induction series. And in this tutorial, we'll be learning about the direction of induced current, the law which describes it, and the experimental demonstration of this law. So we'll be covering the third learning objective. And let's start with the experimental demonstration. So we have this experimental setup in figure 3, a bar magnet and a coil which is wrapped around a hollow cardboard tube, and the ends of the coil, they're connected with a meter to indicate the presence of the current. We have marked the ends of the coil as A and B. To record our observations, we have this table, and the table lists the magnetic pole which would be moving towards the coil or away from the coil. We have another column which shows whether the pole of the magnet is pushed in or pulled out, and the direction of the current which will be induced as a result of changing magnetic field, the induced polarity at end A and B, and we also have a column for the interaction between the magnet, the bar magnet, and the coil. So let's just consider stage 1 of this experiment. So we're considering the north pole of the bar magnet. It's going into this hollow cardboard tube. Because of changing magnetic field, a current will be induced in the coil, and that current will be flowing in the counterclockwise direction. Okay, and you know that when the current flows in the counterclockwise direction, the thumb, it shows the pole of the magnet. So it will be north pole on end A. So when there's north pole at end A, and this is north pole of permanent magnet, obviously you would know the north and north, they would be repelling each other. So the magnet and the coil, they would repel each other. Let's consider the second stage of the experiment. We're using the same north pole, but now we are pulling it out of the hollow cardboard tube. Since we are moving the coil, since we're moving the magnet in the opposite direction, the current will also flow in the opposite direction. Now it starts flowing clockwise, and when the current flows clockwise, the other end, NB, becomes north pole and NA becomes south pole. So NA is south pole, and our bar magnet's north pole is facing NA. So north and south, as you know, they would be attracting each other. So let's just understand the behavior of this coil in the presence of this bar magnet. So when the north pole of the bar magnet is trying to move into the hollow cardboard tube, it is repelling it by becoming the north pole at NA. And when we're trying to pull it out, it's becoming south pole. So it's literally opposing the movement of the magnet, which is producing induced current in it. So this is what Lenz law says. It says that the direction of the induced current is such as to oppose the change producing it. So the change here is the movement of the magnet, which is producing induced current, and this induced current is inducing polarities on ends A and B, and it's opposing the movement of the magnet causing this change. So this is what Lenz law is, and Lenz law is also a form of conservation of energy. So this electricity which is induced in the coil, it is not induced out of nowhere. It is because some work is done to move the magnet. Okay, the magnet is moved back and forth, so you're applying some force. Okay, the force is moving this magnet to a certain distance, so some work is done to move the magnet. So that work done appears as electrical energy flowing through the coil. So it is a form of conservation of energy as well. So let's summarize that the induced current, it flows in a way that it opposes the change causing it, and it is also a form of law of conservation of energy. So I hope you also understood the Lenz law. With this, we completed our series of electromagnetic induction, and I'll see you in the next series of topics. See you.